Hi, so yesterday, or whenever the last time was that we talked together, you learned about Rolle's theorem. Rolle's theorem guarantees that if a function is continuous on a closed interval, differentiable on an open interval, and f of a is equal to f of b, then there is guaranteed to exist. So hold on, a function is continuous, differentiable, you need to also write, and f of a is equal to f of b. Really, really important. Then there's guaranteed a value of c in which the instantaneous rate of change is equal to 0. What that means is f prime of c is equal to 0. Mean value theorem is actually kind of a bigger theorem. Like, this is a more specific one. If you're like, you know what, I want a one-size-fits-all approach, mean value theorem actually even can overtake this one. But this is pretty helpful sometimes too, to recognize that a theorem is being used. We'll talk about that later. So a mean value theorem, think about mean as in an average. So in math class, mean doesn't always mean that somebody is mean and grumpy. Mean is the average, or average rate of change in calculus. That's what we're going to talk about. So if f of x is continuous on a closed interval, differentiable in the open interval, then there exists a point in which f prime of c, so do you see how this is the instantaneous rate of change at c, is equal to the average rate of change over that interval. So the average rate of change equal to the instantaneous. So the reason why I'm saying, well, like this would be, this relates to Rolle's theorem, is let's think about this. If f of b equal to f of a, or f of a equals f of b, f of b minus f of a over b minus a. And let's say this is the same value. So f of b was the same minus f of a. Anytime you subtract the same number, you get 0. So this is saying that the average rate of change, because f of a is equal to f of b, is equal to the instantaneous. So this is really just a corollary, well, it's officially a theorem, but it's a theorem, it's kind of an offshoot of MVT. So this is the mean value theorem. The average rate of change is equal to the instantaneous rate of change. Now let's use it. We consider this function. We've got h of x equal to 3 minus 5 over x. The graph is pictured below. Does MVT apply on the interval from -1 to 5? So this, like every other theorem that we've talked about so far, it's really important that this function is continuous over the entire interval from -1 to 5. Is there any place where this function is not? You can see it on the graph also. I can see at x equals 0, there's a vertical asymptote. Or I could say, well, x cannot equal 0, because that would be in the denominator. Therefore, MVT cannot be applied. I didn't put it in caps, so I'll underline it. Cannot be applied. And the reason is, as h of x is not continuous, and you can't just stop there because it is continuous some places, it's just not continuous on the interval from -1 to 5. So I can't even do it. I'm like, okay, that's boring, move on with life. Does MVT apply in the interval from 1 to 5? Well, we just said that the only place where x could not equal a number, so x could not equal 0, was when in that denominator. Do you see that? I said that whole sentence weird, but I think you get it. The only place where h is not continuous was when x equaled 0. So 1 to 5, all good. So I'm going to say h of x is continuous on 1 to 5. I'm going to go down here and I'm actually just going to find what the derivative is. H prime of x, just to make sure that this is differentiable, even though this looks nice and smooth and all good. By the way, this is h of x. I'm going to go down here and find the derivative. The other way that I can write this function is h of x is equal to 3 minus 5x to the negative first power. If I take the derivative, that would be the derivative of 3 is just 0. -5 times -1 is 5x. Subtract 1 from the exponent. Or I can rewrite that as 5 over x squared. And I can see that this derivative does not exist when x is 0. But again, not on the interval. So h of x is continuous. And I can say differentiable on the open interval. So differentiable on 1 to 5. For mean value theorem, that's all we need. We need a function that's both continuous on the closed interval, differentiable on the open. MVT can be applied. Okay, next one, graphically. Now that we know it can be applied, what does this mean? And I'm going to draw it on the graph. So here, from 1 to 5, so here's my point at 1, 5. MVT says that if a function is continuous and differentiable, then the average rate of change is equal to the instantaneous rate of change. Well, I know if I'm going from 1 to 5, my average rate of change would just be the slope connecting those 2 points. Slope of the secant line, average rate of change. Is there somewhere where if I made a tangent line, here this would be pretty steep, sorry my hand's in the way, here if I made a tangent line, pretty steep, pretty steep, pretty steep, but then somewhere around this area, my tangent line will be parallel to my secant line. Parallel lines have the same slope, so somewhere the slope of the tangent will equal the slope of the secant. I don't know exactly where because this was just a guess. So I did this graphically. What does this mean? So slope of the secant equals slope of the tangent at some c. Or I can say there's somewhere where f of 5 minus f of 1 over 5 minus 1 is equal to f prime of c. And for some c in 1 to 5. So somewhere in here, and it looks like this one is like a 2 maybe, or close to that. So let's try it. It says apply MVT. So what I'm going to do is move up to just about here. And I'm going to say, well, what is f of 5 minus f of 1 over 5 minus 1? F of 5 was 2. F of 1 was negative 2. 5 minus 1 is 4. That's nice. And if I check up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1, yeah, the slope is just 1, so I could have done it that way. There's somewhere where this is going to be equal to f prime of c. So I'm going to take this 1 and set it equal to f prime, which we know f prime, or in this case, h prime. So I really should have changed these to h's if I was... This is why you don't write in pen. So if you decide to live dangerously also, this would have been h, so many h's. Whew. Messed that up. Okay, so this would be, I don't know why I drew that so big, 5 over x squared. This is my average rate of change, was 1. My instantaneous rate of change is my derivative. And now I solve for x. Multiply on both sides by x squared. Square root of both sides. This could be positive or negative because I'm introducing it, but because I want something in the interval from 1 to 5, I'm going to choose the positive. And if I look at this, because I said it was around 2, square root of 5 is 2.23. 2.23. Yeah, that looks about right. We're pretty close. Keep your answer as the square root of 5. If you were going to change this to a decimal of some sort, like if you were going to round this, make sure that you have 3 places after the decimal. I'm going to start being pretty tough on that on quizzes and tests, so make sure you've got 3 places after the decimal. In this one, because it was asking for the value of c, if we wanted to change this to no longer x but a c, you could. Woo woo! Let's do another page. And this one, explain why you cannot apply. Oh, it's so sad. But at least we're getting some, you know, at least we know before we start that we're not going to apply the mean value theorem, so it's not like just like a kick in the face or something. You know you can't use it. Okay, explain why you can't use the mean value theorem. So let's think through this. That means that this function is either not continuous or not differentiable. So now we have to try which one. If I have x to the 2/3 minus 2, any number I can raise to the second power and then take the cube root of it, that's all fine. Any number that I can possibly think of. So I'm going to say f of x is continuous on the interval -1 to 1. That doesn't explain why we can't use the mean value theorem. It's just saying it is continuous. The next thing is this function differentiable? It's the only other condition, so I'm going to probably assume, but f of x is not differentiable, but I'm going to get there in a second. Over on the side, I'm going to take the derivative. F prime of x would be 2/3 x to the -1/3 minus 0. If I rewrite that, I can see the denominator, if I set that equal to 0, or say where it cannot equal to 0, divide by 3 on both sides, x to the 1/3 equals 0. Take cube both sides, I get x is equal to 0. But, and I'm going to say f of x is not differentiable on the interval -1 to 1, so it's the open interval, as x cannot equal 0 for the derivative. So as x cannot equal 0, and then you're seeing this work below. Okay, so I feel like that explains it. I don't have to go back there and say that this is but x can equal 0 on the original function, because I already said it was continuous. So in this one, therefore, MVT cannot be applied. One more. Find the equation of a tangent line. What? It's like coming back to an old friend. We're finding the equation of the tangent line. I wonder if there's a new spin on this. F of x is equal to 2x plus sine of x plus 1. Okay, seems the same so far. On the interval for 0 to pi, at the point which is guaranteed by the mean value theorem. That's fun. Okay, so to find the equation of a tangent line, we need two things: a slope and a point. But before I can even begin, it says at the point guaranteed by the mean value theorem. So the mean value theorem says if a function is continuous and differentiable. This one is. And it doesn't say I have to justify anything, so I don't have to write f of x is continuous on the closed interval from 0 to pi and open differentiable on the open interval. But I could if I wanted. But what I do want to know is mean value theorem says f of b minus f of a, so f of pi minus f of 0 over pi minus 0 would be equal to f prime of x for some value c in that interval. F of pi, so over here, f of pi, 2 pi plus sine of pi plus 1. That means f of pi would be 2 pi plus sine of pi is, this is my sine curve, is 0. So I can just say 2 pi plus 1 minus f of 0, 2 times 0, plus sine of 0 plus 1. 2 times 0 is 0. Sine of 0 is 0. 1. Over pi. If I keep going with this, this would be 2 pi plus 1 minus 1 over pi. Be 2 pi over pi, which is just 2. This is not my answer yet. This is just the average rate of change. The average rate of change has to be equal to the instantaneous rate of change. Instantaneous rate of change, also known as derivative. The derivative of 2x plus sine of x plus 1, do that. Did you get 2 plus cosine of x? So I know this has to be equal to 2 plus cosine of x. Now I solve for x. Subtract on both sides and I get 0 is equal to cosine of x. I'm only going from the interval from 0 to pi. Cosine, in my head, you could be doing this different ways. Maybe you're thinking of the unit circle, but I think of this and I think of the cosine curve. Cosine of what gives me 0? And I'm thinking, okay, this would be 0, this would be 2 pi. Here's pi. Cosine of pi over 2 gives me 0. That means my c value is pi over 2. If I need a slope and a point, I would say f prime of pi over 2. This will give me my slope. So f prime we knew was 2 plus cosine of x, so 2 plus cosine of pi over 2. And really, we've already found this, but you'll get there. 2 plus cosine of pi over 2 will be 2 plus 0, which is just 2. And some of you might have already gotten there because you're like, hey, this is the slope of the tangent already. We said that it was going to be equal to the slope of the secant. We already got 2. But if you didn't and you found 2, that's okay. So this is my slope. So when I do y minus y1 is equal to m times x minus x1, we did that part already. My x value we know is pi over 2 because we found this here. And then the last thing you need to do is just find the function value. So the function value at pi over 2. 2 times pi over 2. I'm going back up to this original function. Plus sine of pi over 2. Plus 1. Pi plus sine of pi over 2. The way that I think about it in my head is I think, okay, this is 0, this is pi, sine, this would be 1. You get pi plus 2. Make sure you put in parentheses if you write it this way, but I'm just going to keep it as pi plus 2. This is my final answer. This is my equation of my tangent line. The mean value theorem guarantees that if a function is continuous on a closed interval, differentiable in the open interval, then there is guaranteed to exist a value of c where the instantaneous rate of change. This is the slope of the tangent, f prime of x, at x equals c, so I can even say f prime of c, is equal to the average rate of change, f of b minus f of a over b minus a. Ta-da! Thanks for working with me. Thanks for doing this. I appreciate you. If you need anything at all, please let me know. Thanks so much. You're great. Bye.